Hi everyone, my name is Zhou, and I'm excited to present our work on in-depth mouse from Autodesk research that integrates desktop mouse into virtual reality. VR is usually considered as an independent medium separated from our regular desktop environment. There has been recent effort trying to integrate them into one unified environment. In VR, users can stream their desktop applications into the virtual workspace. In AR, users can extend their limited display with additional 3D models in the augmented physical space. In either way, it is promising to support productive knowledge work, especially for applications with three-dimensional extensions. Users can stream existing desktop interface into the virtual environment by rendering 2D windows and 3D models at the same time, creating a virtual workspace that enables users to work productively everywhere with head-mounted displays. They can alternate between the 2D and 3D content, such as selecting a face on a 2D model and then followed by texting text or clicking a button in a 2D window. Interacting with 2D desktop interfaces relies on accurate, stable, and comfortable input. This is usually provided by traditional pointing devices such as mouse, but is not supported well with the current approach of midair pointing, with controllers and hand gestures for low fatigue and high precision selection, especially compared to desktop mouse. Directly integrating the mouse into VR is difficult and can cause several problems. For example, a user may experience double vision when aligning the cursor with an object at a different depth. Converging the eyes on the cursor will produce two images of the object, while converging on the object will produce two images of the cursor, making it difficult to select and cause discomfort, which is referred to as the diplopia problem. In another example, a user moves the cursor from one object to another. Changing the viewpoint results in a different perspective and may cause the mouse movement back to the wrong spot, causing confusion and making it difficult to select, which is referred to as the perspective problem. Or when the sensitivity of the control is improperly calibrated, a user may have to clutch multiple times to travel to a distant object, or it may just be too sensitive to select something precisely, which is referred to as the sensitivity problem. This can be particularly problematic to select a small object in a large display space. Conceptually, this is trying to answer the question that if users need to select a small object, say a vertex in a 3D model, how small it can be, where we can safely render it in VR to make it visible and easily selectable by the mouse. To answer these questions, we look at capacities of human vision system that has constraints with a minimum visual angle to distinguish an object or read a character. VR displays have additional constraints with everything rendered in pixels. It can render an object as small as 1 pixel or display a legible character with several pixels. These visual angles are the constraints of the smallest object to be visible or legible. We can plug these constraints into a simple geometry relationship to calculate a usable range that defines the positions where we can safely render an object with a small size to be visible or legible, either constrained by our visual or device resolution. For example, let's say we have a 2 cm target to be rendered in a headset like an Oculus Quest 2. The red region shows where we can safely render it to be legible, with the dark region further indicating the influence from the field of view. To make it easily selectable by the mouse, we need to determine how much the hand movement can lead to a reasonable amount of cursor movement to reach the target. This is usually referred to as determining the CD gain or control display gain. We developed a CD gain tool that computes the range of CD gains that users can use based on the devices in use. For example, with a Quest 2 and a standard mouse of 1000 dpi, it gives us the range to use in VR. This addresses the sensitivity problem based on the device in use. To address the other two problems, we developed Depth-adaptive cursor, a mouse-based pointing technique for 3D selection with depth-adaptation. Depth-adaptive cursor interpolates the cursor depth by inferring what users intend to select based on the cursor position, the viewpoint, and the selectable objects in the scene. It automatically adapts to the depth of the objects nearby and moves continuously in 3D. It works in three simple steps. First, we update the cursor ray's origin by attaching it to user's viewpoint. Then we update the cursor ray's direction based on the mouse movement. We use the CDGAN determined by the CDGAN tool to convert the hand movement into the cursor ray's angular movement. If the cursor ray intersects with an object, we set the cursor depth to be the depth of the closest intersection. If not, we project objects into a Voronoi diagram and use objects nearby to interpolate the cursor depth. The result is a control mechanism consistent to a regular mouse with depth adaptation that adapts to the depth of objects nearby. Since it moves continuously in 3D from the viewpoint, it by default resolves the diplopia and the perspective problem. In a user study, we evaluated the approach using a 3D pointing task that required users to select between a 2D plane and 3D targets, and a data analysis task that requires users to analyze 3D scatter points in a virtual workspace and compare it to a version without depth adaptation. We found the depth adaptation improved the completion time of 3D selection, and in particular for small and distant objects in the scene. The difference in completion time with or without adaptation is more evident with small target size and large target depth. Similarly, we found the depth adaptation improved the selection error with red dots outside the green circle as error clicks. Participants made fewer mistakes with adaptation and they benefited more when selecting small and distant objects. This indicates that adaptive cursor could be critical for tasks that require precise 3D selection. More results and discussions can be found in our paper. Thank you.